Today's lesson is called definite integrals. Last time we talked about how to approximate the area using rectangular shapes, and the width of the rectangular shape, we call that a delta x. And we could either use left endpoint, right endpoint, or the midpoint of the rectangular shape to approximate the area by adding those rectangular shapes. Today, instead of approximating the area, we're going to try to find the exact value of the area. One thing that we talked about last time was having more rectangular shapes in a bounded area will produce a little bit more accurate answer, because those gap will get smaller and smaller and smaller and smaller, where eventually it's going to disappear. So we're going to combine with the previous topic called limits so that the rectangular shape will be infinite amounts. So instead of having 5 or 10 or 100, we're going to take a look what happens if you have a rectangular shape approaching infinity. And eventually, because of its infinity, those small little gap will eventually disappear, allowing us to calculate the area. Now, when we're solving for the area, again, we have three options. We could use a left endpoint, right endpoint, or midpoint. Because the rectangular shape will approach infinity, any one of those methods will get you the same answer, because the gap will eventually become smaller regardless you use a left endpoint, right endpoint, or midpoint. So my suggestion is using the easiest one to solve, which will be the right endpoint. So let's look at an example how to find the areas. Find the area of the region lying between the graph of 4x minus x squared and the x-axis between x equal to 0 and x equal to 4. So we have a parabola. X-intercept is at 0 and 4. And our goal is to figure out this area. So once again, we're not going to use rectangular shape to approximate. We're going to find the exact value. So delta x, in this case, is 4 over n. And we're going to try to use the easiest method, which is a right endpoint, because you only have to multiply by I instead of I minus 1 or I minus 1 half, depending on if you use left endpoint or the midpoint. So this will become 0 plus 4I over n as a sequence. So the area will equal to limit as n approaches infinity for 4 over n, which is our length, summation of I equal to 1 to n number rectangle for f of 4I over n. So it will be summation of I equal to 1 to n, 16I over n minus 16I squared over n squared. I'm going to try to make this common denominator, so I'm going to put 16in over n squared instead of writing as 16I over n. So now we're going to factor out not only n squared in the denominator, but 16 is also exists in both terms. So I'm going to take a 16 over n squared, making it a 64 over n to the third, sigma of I equal to 1 to n, in minus I squared. So limit as x approaches infinity for 64 over n to the third times n plus 1 times n over 2 minus n times n plus 1 times 2n plus 1 over 6 Now I'm going to try to make this common denominator right away. So everything is over 6. So that means on the first term you have to multiply by 3. So we'll have 3n to the third power plus 3n squared minus 2n to the third minus 3n squared minus n. Again, these are negative because you're distributing the negative 1. So now we have limit as x approaches infinity 64 over n to the third times n to the third minus n over 6. And we have limit as n approaches infinity 32 over 3 minus 32 over 6n to the second power. So if you apply the limit as n approaches infinity, first term will be 32 over 3. Second term, notice that the denominator is getting bigger and bigger and bigger as n gets bigger, which means it will be 0. So your final answer will come out to be 32 over 3, which is our area of 4x minus x squared, bounded by x-axis and x equal to 0 and x equal to 4. Number 2, it says evaluate the definite integral of 3x from 2 to 4. We talked about definite integrals, another way to say area. So just to see as a graph, here's a graph of 3x. Let's pretend this is 2, this is 4. Our goal is to solve for this area. This is a trapezoid, so it might be easier if you use geometric shape to solve it, but we're going to solve it as a limit. So limit as n approaches infinity for 2 over n, because the delta x was 2 over n. And once again, we're going to use a right endpoint because that's the easiest. It'll be 2 plus 2i over n, which the sequence will come out to be 2n plus 2i over n. So now we have sigma of I equal to 1 to the n f of 2n plus 2i over n. Don't forget our f of x is 3x. So it's limit as n approaches infinity 2 over n sigma of I equal to 1 to the n 3 times 2n plus 2i over n. So we have sigma as I equal to 1 and 6n plus 6i over n. And we could factor out 6 over n in this case. So we'll have 12 over n squared n plus I is what you're left with. So now let's plot the sigma. So 12 over n squared times n plus n times n plus 1 over 2. So limit as n approaches infinity 12 over n squared times 2n squared over 2 plus n squared plus n over 2. I made it as 2 over 2 because the common denominator. Now I'm going to distribute and simplify as limit as n approaches infinity. You're left with 12 over n squared times 3n squared plus n over 2. (18) plus 6 over n. So as limit as n approaches infinity, 18 plus 6 over n. N will get bigger and bigger, which means the 6 over n will approach 0. And the answer will come out to be 18 as the area of that trapezoid. So as a conclusion, in order to find the area of f of x bounded by x-axis from a to b, we could use a limit as n approaches infinity of delta x, which is the width of the rectangular shape, and summation of its length. Or another way of writing it will be integral of f of x from a to b.